Good morning. Good afternoon, everyone. My name is Brandon Steve, and I am a graduate student at Ball State University. Today, I'll be discussing my research, a novel bismuth oxyhalide carbon quantum dot photocatalyst for the degradation of trichloroethane. Um,
Click in the screen. There you go.
there we go. All right. So TCE have been widely used in U.S. industry for more than a century. As a result, it is one of the most common groundwater contaminants in the U.S. It is a known carcinogen according to the U.S. EPA and the World Health Organization, and is considered a carcinogenic by all routes of exposure due to its greater density than water, poor water solubility, and low Henry's law constant. TCE tends to contaminate groundwater systems rather than surface water systems. As you can see in the map provided by the Environmental Working Group, the Great Lakes region is one of 3 areas that has substantial and widespread TCE contamination, with numerous sites that are greater than the EPA drinking limit of 5 parts per million, illustrated by the bright red colored dot. If we move over to the schematic of the photocatalyst, we can see that for Roman numeral 1, when a photon of sufficient energy strikes the photocatalyst, an electron is excited from the valence band to the conduction band, where either Roman numeral 3 or 4, we can have respective reduction or oxidation, either of the species in question or the formation of radicals that attack the species. Unfortunately, by Roman numeral 2, we can see that that excited electron can relax back down to the ground state and release heat or light before doing any photocatalytic work. And this has been the downfall to many photocatalysts. My research involves using the semiconductor photocatalyst of bismuth oxyhalides, which are both photoactive under UV and visible light. They are inexpensive, possess low toxicity, and are easy to synthesize, along with sensitizing them by carbon quantum dots. Carbon quantum dots are small spherical carbon nanostructures, generally between 1 and 10 nanometers. Due to the wide array of precursor materials that we can see here, they are lack a defined chemical structure, but they do possess a conjugated interior, as well as a surface containing carbon-oxygen, carbon-carbon, and carbon-nitrogen functional groups, which can vary from the temperature of synthesis and precursor methods and ratio. Bismuth oxyhalides were synthesized using a surfactant-assisted hydrothermal method, and we do use a hydrothermal-based method for carbon quantum dots as well. Experiments were performed using initially the rhodamine B dye under 300 watt of simulated sunlight, and TCE degradation experiments were performed under that same light. Bismuth oxychloride was effective at degrading TCE, as you can see by the third of the 3 charts. However, additional research needs to be done on bismuth oxybromide and bismuth oxyiodide. For catalytic activity under bismuth oxychloride, under rhodamine B, bismuth oxychloride showed the most photocatalytic potential, followed by bismuth oxybromide, and third, bismuth oxyiodide. However, it is worth noting that with calcination, the catalytic activity of bismuth oxyiodide greatly increased. These new composite materials are an effective means at degrading volatile chlorinated compounds and other similar compounds.
1 minute, Brandon.
I think I'm done.
That was good timing then.
Yes.
Thank you very much.
Before I do go, I will say one more thing, is that there are some additional data. If you go to the, I'm sorry, where is it again? WOVU?
Whova, yeah.
Whova, yes. We can download additional slides. You can see some additional data that I was unable to fit into this presentation. Thank you.